welcome today as our colloquium speaker, Professor Catherine Johnston. Catherine received her PhD at UC Santa Cruz, after which she moved on as a postdoctoral member of the Institute for Advanced Studies at Princeton. After that, she was first faculty member at Wesleyan College, and then moved on to Columbia University, whom some of you might know, in the neighborhood. And now she's been there as department chair since 2014. Her theoretical work has impacted large areas, including what we call galactic archaeology and galactic cannibalism, meaning how the Milky Way formed and grew over time. And in particular, her research has impacted understanding the properties of the elusive dark matter, which of course, as we know, is the most dominant matter component in the universe. So today she'll tell us more about her research, and the title of her talk is Dark Matter and Stellar Halos.
Okay, great. Thanks very much, Mariam. It's always fun to come down here and see you all. So indeed, I'm going to talk about dark matter halos, and also stellar halos. And I'm going to talk about how we can use stellar halos to learn about dark matter halos, among other things. You may not have heard much about stellar halos before. So starting from some galaxy in the universe, you may be used to seeing an image like this of what the galaxy looks like. And of course, the dark matter halo that surrounds such a galaxy, you probably know, we believe to be extended 10 times further in radius than the bulk of the galaxy that you see, and also to be of order 10 times more massive. So most of the mass in this structure is not in the little part that we can see. So what I want to talk about is actually what's out here in terms of stars. And we call this the stellar halo of a galaxy. 99% of the light of a typical galaxy like the Milky Way would be contained in the central part. So there's 1% of the light of the galaxy, a small dusting of stars spread out over a huge volume here. This actually makes stellar halos really hard to study because, as you can imagine, they're very low surface brightness. So one question you might ask yourself is, why bother? And I'm hoping to give you several answers to the question of why bother studying 1% of the light in the universe. And actually, it's not even 1% of the mass. It's like 0.01% of the mass in the universe. In itself, it's inconsequential, right? It's inconsequential in the star formation history. It's inconsequential in terms of its influence on matter formation. Structure formation. So one answer to why bother in order to tell you that story, let's go back and just look at dark matter itself. This is a simulation from the Santa Cruz group. It's the Via Lactea 1 simulation, actually. And this is showing you how we think a dark matter halo like the one that surrounds the Milky Way galaxy may have formed. And the key things to see here is the main dark matter halo forming here, but also all these smaller dark matter halos that are constantly interacting with this main dark matter halo. And as you get to z equals 0, what you'll see is it's not that all these little dark matter halos have disappeared. Many of them have been agglomerated into the Milky Way, the main halo, but many still remain. So you should think of this, there'd be a tiny little galaxy. It's giving you a sense of scale over here. We're zooming in here. There'd be a tiny little galaxy in the middle, surrounded by a smooth dark matter halo, but filled, about 10% of the matter in the dark matter halo would be in these lumps. And the point about this picture,
These points just indicate mass?
Exactly. So the light indicates mass, actually, in this case. So it's more dense, the more intense it is. The more dense parts indicate more mass.
So are these things visible?
Right. So the Milky Way is visible because we have a little dusting of stars here.
Right.
And the more massive ones of these would be satellite galaxies. And then many of these are invisible. We don't yet know if they exist or not. I'm going to talk a little bit about that today. Okay?
So there's a simulation that includes only gravity, also some of the detail of astrophysics in terms
Right.
of things being blown out by supernovas.
So this is a dark matter only simulation. So it's only including the dark matter. So there's no matter like you and me. So there's no explosions. There's no radiative physics at all. It's just gravity, mass and gravity. Okay? So the reason why I wanted to show you this simulation was to show you what the dark matter is doing. And as we just pointed out, inside many of these dark matter halos would be a dusting of stars. So what happens to that dusting of stars as these objects fall together? One clue to that is if we look at, has come out from observations. By the way, we call this process hierarchical structure formation. So if I say that, hierarchical structure formation, I'm meaning the dark matter starting in small lumps and falling together. So if we look observationally around galaxies, in the last 15 years or so, we've come up with some stunning images that gives us some clues here. This is actually looking around our nearest neighboring galaxy, the Andromeda Galaxy. And the image you might have seen of Andromeda, it's a beautiful disk galaxy. Images you would typically have seen would extend this far. And what this is, it's not actually an image, it's a star count map. So what the astronomers did to make this image was they found stars that were at the right distance to be members of Andromeda, and they counted the numbers of stars in each of the little pixels of this map. In fact, each square represents a single observation. And so you can see they've taken many observations, and within each square they've counted the number of stars. And what you're supposed to see is way beyond the edge of what we would say beforehand was an image of Andromeda. You see many, many stars. And these stars don't completely fill what we know must be the dark matter halo here. There's a small dusting of stars throughout, but they make these structures here. You can see sort of shell features here, a stellar stream here. There's another stream coming down here.
What is the halo end? Is that the green circle?
Well, so the halo never ends, but
It just dies out.
But yeah, you would expect, so this is roughly 300 kpc, you would expect the edge of the virialized part of the dark matter halo to extend at least to 150 kpc beyond probably 200 or 300 kpc, okay? So the little light galaxy is here, the dark matter halo is way out here, and what you're seeing here are overdensities in stars in the stellar halo, that 1% of the light. And the way we think this connects back to the previous image is what you're seeing here are the remnants of accretion events. You can't see the dark accretion events, but you can see the stars that have been torn from those dark satellites and are left over in these accretion events. And this sort of map, the reason this is so exciting is we were unable to see these structures around Andromeda until the last 10 to 15 years or so. You can actually do the same thing for the Milky Way galaxy.
It's just better detection.
It's because you're able to count the stars at very low brightness.
Right.
Exactly.
That's done with telescopes?
This was done with the CFHT. This was done with the CFHT, Canada, France, Hawaii telescope, which is in Hawaii. So it's a ground-based telescope. Okay. This next image I'm going to show you is of the Milky Way galaxy. But of course we have, actually, can we dim the lights? We dim the lights a little bit. It doesn't need to be completely off, but this is of the Milky Way galaxy. Of course, if we sit inside, this is good. This is good. This is okay. This is good. Nobody go to sleep. No, we have an internal view of the Milky Way, which is why I showed you the other image first, because you have to imagine here what you're doing is you're looking at roughly half the sky. This one is from the Sloan Digital Sky Survey. NYU is actually a member of the Sloan Digital Sky Survey. And the faculty at NYU tend to study the millions of galaxies in the Sloan Digital Sky Survey. But in order to make those images of millions of galaxies, you have to take images of millions of stars. So you can also use the Sloan Digital Sky Survey to very carefully count where distant stars are around the Milky Way. And this is showing you not what's in the main disk of the Milky Way. This is beyond the disk of the Milky Way. The colors represent distance, but the important thing I want you to get here is this is not uniform. There are streams of stars here. This is a major Sagittarius stream, the Orphan stream, GD1 stream, Palomar 5. You don't need to remember the names. The point is these are all, again, signatures of the process of hierarchical structure formation. So the fun thing that's happened in the last 15 years is that we've had this theory of hierarchical structure formation for a long time. We have been able to see dramatic effects of hierarchical structure formation before 15 years ago. But what's happened in the last 15 years is for the Milky Way and Andromeda, we've been able to see very small events, and we've really got a sense that hierarchical structure formation really occurs. And that's been a dramatic change in our thinking. And that is from looking not at the 99% of the light in a galaxy, but looking at the 1% of the light that surrounds the galaxy. So what I want to do today is to talk a little bit more of why that 1% of light can be interesting as a tracer population and how you can use it to probe other things as well. And it's motivated in part by prospects of future surveys coming up. I'm just going to mention few of them in passing to give you a sense of context. First of all, I can't give this talk without mentioning Gaia. Gaia is a European satellite. It's going to measure the positions of billions of stars in the Milky Way so accurately that it will be able to derive distances to them really well, and it will be able to derive their motions tangential to our line of sight. So the exciting thing about this is going to give you a 60 phase space map of the nearby Milky Way.
How does it know the distance, or is there lots of different...
Parallax. It's the parallax effect. Okay? So you have to measure the angular position very accurately. So this is a revolution in how well we can measure angular positions on the sky. Looking further ahead, there's the Large Synoptic Survey Telescope. The relevant thing for this talk is it's going to be able to survey millions, hundreds of millions of galaxies, and it's going to take images over and over and over again. If you add all those images up, you're going to be able to reach really low surface brightnesses. 29th magnitudes per square arc second, I'm sure that means a lot to you, right? The images I showed you in the star count maps would go a little more than a factor of 10 deeper than this. So this is not as deep as the images I showed you for the Milky Way and Andromeda. But nevertheless, it's deeper than is standard today, and we'll be able to get these images for millions of galaxies. So using this, we will be able to go beyond just the Milky Way and Andromeda and start looking at small accretion events, the tiny tail of hierarchical structure formation for millions of galaxies. WFIRST is a satellite, and it's going to be able to make images like the ones I did show you for the Milky Way and Andromeda. So this is comparable surface brightness for hundreds of galaxies. So we'll be going from a sample of 1 or 2 galaxies where we can see what hierarchical structure formation has done. And we can say, oh, well, that's fun. It's kind of hierarchical structure formation. We can go to samples of hundreds to millions. And that means we can start making quantitative statements beyond it kind of matches what we expect. Okay? So there are 4 things that I could talk about today. It won't be terrible if we don't get to them all. But part of the reason I'm telling you what they all are now is if we don't get to them all, you can tell me at the end, maybe in discussion afterwards or over drinks or whatever, we can talk about the ones we don't get to. So I want to talk about measuring orbits of galaxies in the universe using stellar halos, making 3D maps of the Milky Way's dark matter halo. I also want to talk about how you can actually measure orbit structure and find signatures of chaotic orbits in the galaxy and regular orbits in our galaxy. And the last one I really wasn't going to put in, but I thought this audience might be particularly interested in how you can find the lowest mass dark matter halos, the ones that don't contain stars. We don't think they contain stars. So if we start with orbits of the galaxies in the universe, I just want to take a step back for it, because you're not all astronomers, inconceivable as it may seem, but the idea of measuring orbits of the galaxies in the universe is actually very exciting, because we cannot measure orbits in astronomy, because we don't have a 6-dimensional picture of the universe or 3-dimensional picture typically, right? You typically do not know the distance to something very well, and even if you know the distance and you can measure the line of sight velocity from Doppler shifts, you cannot typically measure the sideways motion. We would call that proper motion. Now, I just told you about this mission, Gaia. It will be able to do this for billions of stars in our galaxy. Fantastic. But if you look at any other galaxy, satellite galaxies around our nearest neighbor, Andromeda, or galaxies beyond that, it's inconceivable that you can actually measure how things are moving other than towards or away from you. It's completely inconceivable. So this is why I'm excited about this idea. And the idea is fairly simple. David Hendel, grad student at Columbia, is leading this work. The blue represents the disk of our galaxy, just to give you a sense of scale. The black particles are particles interacting via gravity. So you should think of this as dark matter and stars mixed up together. We haven't worried about that very carefully. What we've done is we've started with a ball of stars. Let's play it again. We've started with a ball of stars interacting via self-gravity. It's using an n-body simulation. And if you let that ball fall in on an orbit that's not too radial, fairly circular, then what happens is that ball disrupts is you end up with these streams of stars, which I hope you think are fairly reminiscent of what I showed you in the observations, right? If you throw the exact same ball of self-gravitating particles in on a more radial orbit, you end up with something that looks more morphologically distinct. And we would call these shells. So these we would call streams, and these we would call shells. And the idea behind this project of measuring orbits is to exploit this difference. So simply put, it's not that you measure individual orbits. It's that if you look at, we use LSST, we look at millions of galaxies. And we can count how often we find shells and how often we find streams. And that's going to tell us the orbit distribution in the universe. In fact, we can do this without actually measuring motion at all. We do it purely morphologically. That's the idea. If you want to know where this comes from in a little, I thought you might be interested in the dynamics a little bit of what's going on. So there's a few illustrations here. Here's a ball of particles in a simple potential. This ball of particles, we've slightly changed. We've kept all the orbital energies the same of all these particles, and they have slightly different angular momenta. If you integrate this forward in time, the ball gradually spreads out. And you have to remember, so this is, on galactic scales, we expect these galaxies to go around tens of times during the lifetime of the universe. So it is interesting to think just a few orbits. Okay, so as you go around, the ball spreads out. And what you see is if you make just tiny changes to angular momenta, this is in a perfectly spherical potential. If you make tiny changes to angular momenta, the ball tends to spread out so it forms something that you can imagine looking like a shell, which is especially apparent at the apocenters of the orbit. And this is due to angular momentum differences. If you now take a ball and keep all the angular momenta the same and just put in small energy differences, you see the ball spreading out. And in this case, it forms something that looks more like a stream along the orbit.
What's the dynamics?
Well, so sorry. This is just Newton's law of gravity and integrating forward in time.
This is classical Newton.
Yes, it's just gravity. Just gravity. It's very simple. We've just assumed, we've assumed some potential here. It will have an extended mass distribution. It's not a point mass, which actually you know because of the precession, right? It's an extended mass distribution, but it's just gravity.
Is that extreme?
Yep. Which extreme?
That orbit, it's not even close to an ellipse. I mean, it's
Yeah.
far away from an ellipse.
Yes. Yes.
So that's not just exaggerated to show us the effect.
No.
That's how big it is.
Some orbits can look like this. So you can get some orbits which would, in an extended mass distribution, the only closed orbit would be, well, depending on the mass distribution, would be a circular orbit. And then the eccentric orbits have pericenters, their apocenters precess, unlike the ellipses. And in the universe, you expect a range of types of orbits. But our extended dark matter halo is going to make you have rosette orbits instead of ellipses. Does that make sense? Okay. So you can actually calculate what's going on here. You can write down simple analytic expressions to characterize this. And if we go through a couple of these terms, this, delta psi, this is telling you the angle between apocenters, right? So the angle between successive apocenters or successive pericenters. For Keplerian orbit, this is 360 degrees. For the rosette, it's less, right? That's why you get the precession. So this is telling you a precession rate per orbit. This is the orbital time period. These are the spreads in energy and angular momenta in our ball of particles, right? So given a given spread in angular momenta or energy, you expect some angular spread at the end. It depends on time through the number of orbits you've gone through. That makes sense. There's more spread. It depends pretty linearly on time. And then the amount of spread you get due to angular momentum differences is due to the difference in the precession rate between orbits of different angular momenta. And the amount of spread you get in energy is due to the different orbital time periods. It turns out in a purely spherical potential, the difference in orbital time periods mainly depends on energy and is pretty much independent of angular momentum. Not strictly, but almost. And the difference in precession at a given energy depends on angular momenta alone. And that's what gives you these two types of spreading. Okay? What I'm saying here is I can show you qualitatively what happens with differences in energy and angular momenta. I can also make a quantitative estimate for different energies and angular momenta of how much spreading you get along and perpendicular to the stream.
And in your movie,
yes.
The one on the right, where
yes.
more spherical and
yes.
The shells had a distinct structure. Was that because there was more than? It looked like there was just one system that was
Absolutely right. So that's fun. You know, we're not going to get through this talk, just to warn you guys, but this is fun, right? You having fun? That's all that matters. So what you're seeing, should we show the movies again? I'll show the movies again. You don't actually want to see the end of the talk. So what you're seeing here, you are seeing the particles are sorting in energy along the orbit, right? Because they have different time periods. So what you're seeing is that leading this are going to be the particles with the most tightly bound. They're going to have the smallest apocenters. And the ones that are least tightly bound, trailing it, are going to have the largest apocenters. So you get interleaved shells because they've sorted themselves in energy. So at a given, it's fun, right? At a given phase, you're seeing particles of the same energy. So they have the same apocenter. But those apocenters systematically differ as you go along the stream. Does that make sense? Okay. Okay, so sorry, I described these two angles we calculate to understand when we expect to see a stream or a shell, or in other words, to understand differences due to energy and differences due to angular momentum. And this we expect a signature of a shell, and this is going to cause streams. There's another difference, another thing that you have to take into account. So if we go back again. Particles tend to hang out at apocenter, Kepler's third law of motion, right? Particles tend to hang out at apocenter. What that means observationally is you're more likely to catch your stream or your shell around this phase of the orbit than this phase. And so there's a limitation observationally that the stream on the eccentric orbits can't be much longer than this length. What you tend to see is you see a stream here and then a gap and then a stream here. So this last limitation is that the length of a stream is going to be less than the angular size of a single petal of the orbit. Let me put this all together pictorially for you, right? Oh, sorry, I forgot about the animations. If we put this together, what it means is for a given simulation that I can run, this simulation, I know the mass of the satellite, etc. I know the change in energy and change in angular momentum that these particles have, the spreads that they have. So I can predict how wide a shell should be in the simulation in angular size as a function of time from the formula I showed you previously. I can also predict the length of the stream, which, as I told you, should get cut off eventually when the stream exceeds a single apocenter. This is the sort of angular size of the apocenter. What you can see is that typically energy differences cause a much faster evolution. You tend to see streams much more easily than shells. And what you're seeing here is you're seeing at about 3.4 gigayears, about here, you can see that the stream, size of the stream is predicted to be larger than the size of the shell. And so here I would not expect to see shells. Later on, this is at 7.2 gigayears, so off the screen, the size of the shell exceeds the size of the stream. So in this case, you can see these streams, right? But you're starting to see the appearance of shells in this image, right? And this is for a given mass satellite. We can do the same experiment for a higher mass satellite. And in this case, you start to see the appearance of shells at earlier times. So what we've done here is we've gone from the idea that more radial orbits produce shells and more circular orbits produce streams. That's a very simple idea. And what we've done is we've tried to quantify this by saying, well, so exactly when do you get a shell and when do you get a stream along a given orbit as a function of mass and of time with simple analytic estimates. Once we've done that, we can then ask the question, what will we be able to say with a given set of observations? And we've just done a simple experiment so far. Oh, sorry, let's skip the slide because I was going on anyway. We've done a very simple experiment so far. And what we did was we said, okay, now that we understand when we produce shells and when we produce streams, we can actually pretend that we're going to go out and we're going to count the number of shells and the number of streams we see in a huge sample of galaxies. And we can compare if we have the red orbit distribution versus the blue. What's showing here is the infall velocity, radial velocity, and the infall tangential velocity for a sample of satellite galaxies. So 5% of infall radial velocity. Infall, yes. So the satellite's coming in, here's the main galaxy, satellite's coming in, It's telling you how it's moving this way and this way, right? So 5% of the satellites are within this peak, 33% within this, etc. So there's the red distribution and there's a blue distribution. This is what goes into our calculation. Coming out, we can say what are the number of emerger events that produce shells versus streams. So for the blue distributions, this is the number of merger events that produce streams, and this is the number that produce shells. So for the blue distribution, you get many more streams than shells. For the red distribution, you get similar numbers of shells and streams, right? And the point about this is what we did was assume orbit distributions and come up with frequencies of shells and streams. What we want to do in the long run is observe the frequencies of shells and streams and deduce what the orbit distribution of galaxies in the universe are.
Could you explain again what's the difference between distribution 1 and distribution 2?
We made them up. We made them up. What we could have done, actually the blue distribution is not completely made up. The blue distribution is what you measure in a dark matter only simulation of structure formation. So you could say this is a prediction from dark matter only simulations, but we don't know what the real universe is like. So we're saying, could we tell the difference between this and what made up distributions could we tell the difference between?
And this is a distribution of initial conditions?
Of initial conditions for satellite galaxies falling into the main galaxy. Okay, so this is a thought experiment. This is not real data. This is pretend data. Any other questions on this? Right, so the take-home point is this is a new observational test for understanding how orbits are in the universe. And what it actually means is we can connect back to the simulation I showed you at the beginning of dark matter only simulations and see if we measure the same orbit distribution that is measured in the simulations in the long run. Okay, okay, so that was the orbits of galaxies in the universe. The second thing I wanted to tell you about is an experiment, and I think we'll get to this one sooner, is making a 3D map of a dark matter halo. And actually I can be very specific about which dark matter halo. I'm talking about the dark matter halo that surrounds the Milky Way galaxy. And I should be very clear here, it's going to be a map of one dark matter halo in the universe. The reason why that's exciting is it's the only dark matter in the halo in the universe that will be able to map in 3 dimensions. Again, remember, astronomers have this trouble finding distances, right? So no galaxy can we map in 3 dimensions. You can map dark matter halos of other galaxies using, for example, gravitational lensing, which is wonderful. But again, what you get is a projected map. You're not getting a 3-dimensional map. So even though it's only one galaxy, I'm actually very excited about mapping the 3-dimensional structure of the Milky Way. And I'll show you this image again. To give you a sense of scale, right, we saw this before. This is a cartoon of what a dark matter halo might look like. Here's the Milky Way, and here's us, the sun in the Milky Way. And what I'm going to talk about is using streams of stars like these to probe the dark matter halo. And again, in this case, these streams are very useful almost precisely because they're inconsequential. We really are interested in the dark matter halo itself. We're not interested in the streams. So it would be horrible if these streams actually had much mass, because then they'd distort our answer. Or we'd have to make a more complicated model to make it work. So it's actually terrific that these streams don't have much mass, because they don't mess up the dark matter halo, and we can just be sensitive to that. The other thing that's terrific about them is that they probe way out into the dark matter halo, far beyond the stars in the disk of our galaxy. So they're measuring the dark matter distribution in regions where we can't measure it with disk stars. The other thing, before I go on, when I talk about why 3-dimensional shapes are interesting, I just want to mention that the dark matter halos in simulations are not just spherical halos. You often think of them as just this big spherical ball, but actually in simulations, you can see that they're triaxial in shape. That triaxiality can vary as a function of radius, and the orientation can vary as a function of radius. In principle, I believe that we will be able to measure all of those things for the Milky Way galaxy. or the dark matter halo around the Milky Way galaxy. And again, I'm not sure if there's another galaxy in the universe we'll be able to do that for. The gravitational lensing folks might dispute that. I'm not sure. So anyway, this is just, again, I haven't got the answer for you today. We're working on how to answer that question. This is work that Adrian Price-Whelan, who was an undergraduate here and worked with David Haag for a year before coming to us, has been working on. So what Adrian did was take an old idea that I'd written a small paper on a decade or so ago, and he applied the full NYU statistics head to that idea, which I was extremely grateful for. The idea is very simple. So here's a simulation of an object falling in and tails being stripped off that object, and here again is the Milky Way galaxy. The idea for our potential measure is simply that these stars, right, that we see in streams, there's one great advantage that they have over random stars in the Milky Way's halo. And the great advantage that they have is precisely that they're not random. We've seen that they're part of a stream. The fact that we see these overdensities in streams, actually tells us that any stars in those streams were once all part of the same object. So we use the fact that they're not random, we use the fact that they were once part of the same object to measure the potential of the galaxy. If you want an analogy, a good analogy is if you look at the stars in the disk of our galaxy, they're very sensitive to the mass distribution because, why? Because they're not random, because we know they move on circular orbits. So again, we're exploiting the fact that we know they're not random, we know something more about them. So this is analogous to that, except these stars are not on circular orbits, but we do know that this star, this star, this star, this star, this star, this star were once part of this object. So in the simulation, at the endpoint of the simulation, I make this image by taking x, y, z, vx, y, z, vx, vy, vz, and plotting up this image. In the simulation case, I know how I had represented the Milky Way, the mass distributional potential I put in here. So in the simulation, in theory, I could take the endpoint and I could start integrating everything backwards. And if I did that, what I should find is that these stars would at some point cross the orbit of this object. The orbits of these stars, as I integrate them backwards, would cross the orbit of this object. Now, of course, in the real universe, I don't know the mass distribution. However, we are hopeful that we're going to get this information for stars in the streams, the observed streams. If we assume a mass distribution for the Milky Way and integrate these conditions backwards, and it's the wrong mass distribution, then these stars won't combine with the progenitor object. So to give you an example of that, what we've done is, what Adrian did was just take the endpoint of a simulation and do the backwards integration in the correct potential, and then he did the same thing in the incorrect potential. So this is just a fun illustration. This expanding and contracting ball is the satellite going round and round backwards. And it's expanding and contracting because its tidal radius is getting smaller and bigger. And we're integrating the particles backwards as well from the endpoint and seeing if they cross the tidal radius at less than the escape velocity. That's our recapture criteria. So in this case, you can see you get up to 80, 90% recaptured. So this is the case when you integrate our simulated stars and the satellite backwards in the correct potential. If we just change the mass of that potential by 5%, this is what we get. And you can see that this number pretty much halts before we get to even 30% here. So basically what this is telling us is we've come up with a test statistic of a way of differentiating between potentials. Luckily for me, because Adrian had been trained at NYU, he took this test statistic and thought about it really carefully and came up with a likelihood function. Haag helped us a little bit with this too. Came up with a likelihood function that we could put into an MCMC code. And I don't want to tell you much more about this. I wanted to give you the idea. This is the output from the MCMC code. So we have our parameters of our test halo potential. This is the scale of the potential. This is the velocity scale of the potential. This is the angular orientation. It was a traxional potential, so this is the angular orientation of the major axis, and these are the axis ratios. And this particular test, what I do want to point out, with this particular test, what Adrian pretended is we were observing 8 stars in a stream, only 8 stars, and we had near future observations with Gaia, for instance, and also some observations that I'm taking now with Spitzer for a special type of star called Ira Lyrae. The 2 points I want you to get here is there are only 8 stars, and with realistic observational errors, this is how well we're recovering parameters for the Milky Way. The scales here are really unimportant. What you're supposed to get from them is we're sort of getting few percent errors on the parameters of the dark matter halo. And you have to compare that to what we know right now is we don't know the mass enclosed within about 50 kiloparsecs of the Milky Way to better than a factor of 2. So we're going from factors of a few to few percent, and that's only using 8 stars. And we're going to have hundreds. So we have not applied this to real data yet. By the end of the year, I hope the survey I'm involved with will be wrapping up. The first Gaia data release is the year after. So I'm really hoping we're going to be writing a paper on the 3-dimensional structure of the Milky Way within a few years. So that's fun. Yeah.
You mentioned a number of schemes. So have you considered the interactions between the different schemes? It shouldn't be too much because the network is dominated by the Milky Way. But for example, the essence here will come in the first involved.
Yes. Yes, no, absolutely. So the interactions between the streams themselves, I think you're right, are not important because the mass in the streams themselves is so spread out. The pesky galaxies coming in could mess up the streams. And actually, that's the last part of the talk is really about the dark matter halos messing up the streams. So I stated this extremely positively. In fact, do I have a nice conclusion? There we go. I stated this extremely positively, but there are a number of complications that we did not consider when we were doing this.
Does it matter if you can see all the other side of the Milky Way? I mean, is it destroyed a lot? In the picture, you can sort of see the whole stream, but you can't.
Oh, does it matter if we can't see the whole stream?
We're only going to be able to see like a piece of it, right?
Yeah, no.
Yes,
that's a very interesting question because a number of people are coming up with different methods for doing the same thing, and they involve modeling the stream itself. In which case, you could argue you need to know the density structure very well and be sensitive to this. We actually think it matters less for us because our likelihood function has to do with the distribution when it recombines. It's quite a compact function. So we suspect it matters less for us, but I'm not actually 100% convinced that it does, that we're completely robust against that. So it's a good question. Any other questions? Okay. So I think we probably just have time for this third one. The last one is finding the dark matter halos. This one is not about dark matter, measuring dark matter distributions, but actually I really like this one. I like to state things a little bigger than they actually are. So the big statement of this is, you know how you take nonlinear dynamics classes as graduate student, at least I did, and it was just really fun making Poincare maps and saying, oh, here are regular regions and here are chaotic regions. The way I like to think about this is I think we can use streams, or we think we can use streams, to actually look up in the sky and say, hey, that's a regular orbit and this is a chaotic region of our galaxy. I'm overstating it. But you want to overstate it to get excited about your research, right? So let me give you an idea of where we're going with this. So we've got this image. I already showed you this image of observed streams around the Milky Way. And in particular, I want to zoom in on this one and this one. You see how beautiful and thin these streams are. There's some fatter ones here as well. These ones are extremely well collimated. In particular, if you zoom into this is the original discovery image using star counts from the Sloan Digital Sky Survey of the tidal tails coming from the globular cluster PAL 5. So what's interesting here is to realize, to remember that when you add complexity to a potential, of various forms, then what tends to happen is that orbits diffuse, and orbits in some regions are no longer regular and they can become chaotic. So an interesting question is what could happen to a stream like PAL5? So I actually was looking at this almost accidentally because we were modeling PAL5. So this is work led by Sarah Pearson, and who's a graduate student, and Andreas Cooper, who's a Hubble Fellow at Columbia. And actually, Andreas is an expert at modeling PAL5 in particular. But it turned out that almost by chance, we ran a simulation of PAL5 in two different potentials, just arbitrary potentials. One was a potential for the Milky Way with a purely spherical halo, but it had a disk. So if you add it up, that basically makes an axisymmetric potential. And in the other one, what we had was a triaxial potential, a very specific triaxial potential model for the Milky Way's dark matter halo. And the bottom line of what we found here was in this one oblate potential, we were able to easily find a disrupting model of a satellite that could form thin streams that looked like Palomar 5. However, in this triaxial potential model, it was not possible to do this for realistic tangential velocities. What we would find, we would get collimated structures for a few degrees here. This is the projection of star counts on the sky. You see collimated structures for a few degrees. And then we saw what Sarah termed stream fanning. And we actually, we did not investigate multiple potentials here. We just talked about ruling out this particular triaxial potential. But the implications of this first work, it was a very simple paper, is the question left behind is, of course, well, why is it in this particular potential that we couldn't fit this stream? And what could that be telling us? So Adrian decided to follow this up to try and understand, can we say attribute this to chaos present in the triaxial potential? And I'll talk about how we measure chaos in a little bit. But the bottom line is, the first experiment that Adrian did for the particular orbit of Palomar 5 in the triaxial potential that we had looked at suggested that the chaotic timescale for that orbit was of order 100 gigayears, in other words, 10 times the age of the universe. And therefore, you would not think that chaos was important for orbits in galaxies in the halo of the Milky Way. In fact, this argument has been around in the literature for some time, saying that chaos is not important for orbits of stars in the halo of the Milky Way. Yet we were finding that we could not maintain thin streams, and so we thought that was odd. So what Adrian did was look at this a little more carefully by coding up some machinery for classic machinery for measuring diffusion rates, what are called chaotic diffusion rates of orbits in different potentials. And the way to think about this is if you take a regular orbit in a potential, you can measure something like, say, its distance along the x-axis as a function of time, and it's going to oscillate up and down. If you take the Fourier transform of a regular orbit, what you're going to find is these very well-defined peaks in orbital period space. And so for a regular orbit, these peaks correspond to the fundamental orbital periods. And a regular orbit in a 3 dimensions is going to have 3 fundamental periods. It could be quite a complex orbit. It could be quite 3-dimensional. So more complicated than Keplerian or the Rosette orbits I was showing you before. They can have 3-dimensional shape. But it will have 3 well-defined orbital periods that you can actually derive from this periodogram, basically, or the fast Fourier transform. If you do the same thing in the same potential but choose a different orbit, and you measure x versus time, if it's a chaotic orbit, you will not be able to find the well-defined orbital periods. Instead, you get a Fourier transform that looks something like this. And the reason is because the periods are changing, right? So this does not happen in simple potentials like spherical potentials. Your periods are conserved. In more complex potentials, in triaxial potentials, your periods can change, which means the orbit is changing. It's chaotically diffusing. So what we actually did, or what has been done classically, is define what's called a frequency diffusion time. And to do that, what you do is you look at position x for some very long period of time. It's typically more than 10 orbital periods, a minimum of 10 orbital periods. And then you look at x in a second window of order 10 orbital periods. And you take the fast Fourier transform of each, and you pull out the main, over that period of time, you pull out what is the main frequencies exhibited during that period of time. And you compare the two. So you pull out, using the fast Fourier transform, the orbital periods, orbital frequencies from window 1 and window 2. And the frequency diffusion time is the fractional change in the orbital periods over the time you did the experiment. So this is the classic frequency diffusion time. Frequency diffusion rate. So what we decided to do was to take this rate and just renormalize it slightly to define a time, where we included, well, what is the expected diffusion, what is the expected scale in orbital periods, orbital frequencies for the globular cluster? Meaning, we would expect orbital diffusion to be important for the globular cluster when the frequencies only change by about 1% or so, because that is the difference in frequencies in the globular cluster tidal tail. So that's quite a stringent condition. So that's what this T omega is. And what we did then is we looked at just 3 orbits in what would be called a realistic triaxial potential for a dark matter halo, which is derived from an n-body simulation. So reality in this case is a simulation, it's not the real universe. And we looked at the orbital diffusion times. We looked at 3 different orbits, orbit 1, orbit 2, and orbit 3. And we said orbit 1 we called regular because we calculated that it should have a diffusion time of order 10 to the 8 orbits. A mildly chaotic orbit because it has a diffusion time of 100 orbits, and a strongly chaotic orbit that has a diffusion time of 5 orbits. And for reference, PAL 5 has gone 40 times around the galaxy. So you would expect only this orbit to really change the morphology of PAL 5's tidal stream. This is what you actually see for the regular orbit, and just an XY projection. You see that the stream is perfectly thin after, I think we integrated for 30 or 40 orbits. For the mildly chaotic orbit, you see the stream is thin close to the center, but you see a small hint of stream fanning towards the end. And for the strongly chaotic orbit, you see a large hint of stream fanning. And what we think is going on here, right, so what we were worried about was we didn't expect to see any stream fanning, even in the mildly chaotic case. And so our explanation for this is frequency, again, is frequency diffusion, but it's over time scales that have not been explored before. So the next series of plots is showing you frequencies, orbital frequencies, for the regular orbit as a function of time. For a regular orbit, they don't change, so you just see a dot. For a mildly chaotic orbit, what you see is order percent changes over tens of orbits. And for a strongly chaotic orbit, you see order 5 to 10% changes over the same amount of orbits. So now there are a series of 3 plots where what you're seeing is the individual particles in the stream that we created. What were their orbital frequencies? So this is all the stream particles in the regular orbit. This is all the stream particles in the mildly chaotic orbit. The green is the starting point, the red is halfway through, and the black is at the end. And then the same thing for the strongly chaotic orbit. So our conclusion from this is that we do think that chaos for realistic galactic potentials, for the type of potentials you measure in dark matter-only simulations, is important for tidal streams. We don't expect tidal streams to survive if they're even on even mildly chaotic orbits. The reason those statements were made that chaos was not important for our galaxy is because people had considered chaotic diffusion only on very long timescales, measured it only on long timescales. So what you actually see the periods doing is that they oscillate randomly, and they're performing something like a random walk. So over long timescales, you get a slow diffusion rate, but over a few orbital timescales, you could nevertheless get chaotic diffusion of a reasonable amount, an amount that actually distorts the coherence of tidal streams. So going back to where I started from, what I think this is exciting, why do I think this is exciting? I think this is exciting because precisely because we do see thin streams around our galaxy. And what you can actually say now is you can look at the PAL 5 stream and you can say, that's a regular orbit. You can look at the GD1 stream and you can say, that's a regular orbit. And that reminds me of sitting in nonlinear dynamics and actually making a Poincare map. And if you'd asked me even a year ago, can we make Poincare maps for our galaxy, I would have said, you've got to be kidding me, right? I mean, observe. But I don't mean making a computer. I mean, observe a Poincare map for our galaxy. And that's what now when I see images of tidal streams, that's what I think about. It's a little bit of a stretch, but I like to stretch. Okay, so I think it's a good place to stop here. I didn't get to the last one. The last idea is very simple. I'll just say it, and then we can just take questions. The last idea is a lot of the is what Mariam said. A lot of the experiments I described to you today, we did have a triaxial dark matter halo, right? But we know from the simulation I showed you at the beginning, actually, it's not only a triaxial dark matter halo, it's even more complicated. It's got lumps in it. It would be absolutely fabulous if we actually could count the number of lumps as a function of mass. And we can't because they don't all contain stars. However, if you put a thin stream in there, the lumps are going to perturb the stream. So we can use the thin streams or perturbations, apparent perturbations in the thin streams to count the number of lumps, dark matter lumps in the galaxy. That's the idea. And I'll leave it there and I can take questions. Okay. What is the mass? Oh, the smallest one we know. The smallest one we know would be around dwarf galaxies of the Milky Way, dwarf satellites of the Milky Way. And from the way the stars are moving, within where the stars are, we measure the masses to be about 10 to the 7, so 10 million solar masses. But that's within where the stars are. So if you extrapolate how extended they are, we think even those could be of order 10 to the 9 or 10 to the 10 solar masses. That's extrapolation though. So within the light, it's about 10 to the 7.
I'm just going to ask if that is our knowledge of the Milky Way, different constraints that we presently have. It sounds like with enormous computer power, you would just try a lot of examples and you would do that.
Well, I think, to be honest, right, of course, in Colloquium, you want to present the rosiest picture, right? The truth, the more we think about it, the more complicated it is. Because we have the Milky Way, and you have the dark matter halo. Then you put the dark matter lumps we can't see. But forget about those. You put in the things you can see. The Large Magellanic Cloud and the Small Magellanic Cloud and the Sagittarius Dwarf Galaxy. So we have 3 massive satellite galaxies and more than 30 lower mass ones. These are all going to mess up the picture. So in reality, I think we are going to need to do what you suggest. I mean, I like to propose simple experiments and get wonderful results. But in reality, I think we will need to take those complications into account. I think we'll do a first order sweep, ignoring them, and then we'll try and model everything together in the end. Yeah.
You mentioned briefly at the beginning of the other method, which is gravitational lensing,
Yes.
and all that, and you said, well, that's a projection,
Yes.
so let's not talk about it. But it seems to me one could kind of integrate the information from this and the other. Aren't they sometimes complementary?
Yes, no, I wasn't meaning to be completely dismissive of gravitational lensing because they can do this for millions of galaxies. I'm exaggerating, but a lot of galaxies. So that is the great strength, is that it's... Well, I guess the thing is, we're just looking at the Milky Way. So the Milky Way is one galaxy, and we know that an average, there's a wide, at a given mass, there's a wide distribution in the properties of dark matter halos seen in the simulations. So it's hard to take what we know about the Milky Way and use it as a constraint on gravitational lensing, or vice versa. If we find the Milky Way distribution sits outside the distribution that we're measuring for dark matter halos in general, elsewhere in the universe, that's going to be a problem. And that might be really fun, because it'd be a big problem. But I'm not sure we can inform each other much beyond that.